Chemistry. This is part 2 of the Unit 7 lab. And so, question, do all radioactive elements decay at the same rate? So different radioactive elements are going to decay at different rates, but what if I had 2 atoms of carbon-14? What would happen to them? They would decay at the same rate. So all carbon-14 atoms decay at 5,750 years approximately, but different elements are going to decay at different amounts of time. And what do we call that? What do we call how long it takes for half of a sample of a radioactive substance to decay? So in order for half of a radioactive substance to decay, we would call that the half-life. So what can you say about the ratio of carbon-14 to carbon-12 in living things? And I don't care if you're talking about your cat or a blade of grass or you. What would you say about the ratio or the percentage of carbon-14 compared to carbon-12 of anything alive? It's pretty much the same. And after that substance dies, which one stays the same? The amount of stable carbon-12 or the amount of unstable carbon-14? So the one that stays the same would be the stable carbon-12. It's stable. It's not going to do anything. Whereas the unstable carbon-14 does what? It decays and it decreases, so it gets less and less, and that's what we can look at when we are determining how old something is, or basically how long ago it died. So it doesn't magically happen. It happens through what I talked about in lesson, it was either 7.02 or 7.03. So we talked about how that happens, so I'm not going to go through that again here. And it also happens, there you go, through a beta decay. So basically you have your carbon-14, 6 protons, 8 neutrons. A neutron turns into a proton. So instead of 6 protons, I have 7 protons. Because every time you change the number of protons, what's going to happen? You make a new element. So we have a different number of protons. We change from carbon to nitrogen. And then there's an antineutrino and electron, which you don't have to worry about. All right, section 3. The extent of decay is measured in half-life. All right, so let's say I have 100 atoms, and the half-life is 1 year. So if I have 100, and after 1 year, it's going to decrease by half. It's going to be divided in half, so I'm going to be down to 50. So if we look at here, these black dots represent the fact that I have 100 carbon-14 atoms, and after the half-life of 5,730 years, how many am I going to have left? I'm only going to have 50. And if you notice, the gray dots are nitrogen. It should say nitrogen 14. So now after one half-life, half of my substance is carbon, half is the stable nitrogen. After another half-life, look at this. It doesn't go to 0. Okay, so this is the number of carbon-14 atoms. It started at 100. After one half-life, it was 50. And after another half-life, it doesn't go down to 0. No, that part splits in half. So 50 divided in half is 25. So after 2 half-lives, after about 10,000 years, I only have 25 carbons. And you can also see that in the pie chart. After one half-life, you have 50. Then you take that 50 and divide it in half. If you have another half-life, you divide that in half. So you can see that it goes down a little bit at a time, always by dividing your remaining amount by 2. So after 3 half-lives, now we're down to about 12. We can't have half an atom, so we got to round. So we're down to about 12. 12 divided by 2 is 6. After 4 half-lives, after about 22,000 years, we have 6 left. Divide 6 in half, and what do we get? 3. So after 5 half-lives, after about 28,000 years, we have about 5 of these are still carbon, and, or sorry, 3. Oh my goodness, sorry, 3. 3 of these are still carbon. The other 97 are what? They didn't disappear. What happened to them? The other 97 turned into a stable form of nitrogen. And then it just keeps going down there. Again, you can't have half an atom, so now we have 2 left over, and then it will be 1, like that. Now, of course, if you're talking about a sample like a fossil, we have trillions of atoms. So it's not like we just have 100. We have trillions. So this is on a much larger scale, but it still represents that you always divide the current number in half. And how you can do that is by using this equation. N, meaning the number of half-lives, equals the natural log of the quantity 1 divided by the fraction remaining divided by 0.693. No, you don't need to know that. Ooh, ooh. That's right. That was worth an ooh, ooh. Don't have to know that because we can figure it all out logically, which I love about half-lives. Honestly, I don't even remember this equation. We think it through. So, the fraction of molecules that we started with. So, if we started with 1, or we can think of it as 100%. All right, so if we start with 100%, it's going through 1 half-life. So we divide it in half, and that equals 0.50. That's how much is left. So 0.50 is what percent? 50% is left over. How many years was that? So if this is carbon, we're saying every half-life is 5,750 years. All right, so after 5,750 years, we started with 100%, now we only have 50%. If I started with 1,000,000 molecules, how many would be left? So I started with 1,000,000, I divided it by 2, I have 500,000 left. And we reduced it by a half, or 50%. Now, the next row, you basically have to imagine an arrow saying, okay, now that we're done with this row, let's go over here and start the next row. Okay, so we're finishing this up and then we're going to keep going. So now we're starting with 50%. Okay, we're starting with 50%, divided by 2. What do we have left over? 25%. How many years would that take? Well, each half-life is 5,750. There were 2 half-lives, so that means 11,500 years have gone by. How many molecules? Well, after 1 half-life, we had 500,000. So now we're going to divide that by 2, and we have 250,000 molecules left. And that's a quarter of what we started with, which you can get by taking a half times a half, or 1 times 2 to the second. All right, let's do the next one. So we're down to 25%. Okay, and it's going to go through a half-life. So what would our answer be? It would be approximately 12.5%. And how many years would that take? So this is the 3rd time we've done it. And so our answer, we did 5,750 times 3, about 17,250 years. All right, so now how many molecules are left? Well, we're at 250,000. We did another half-life. So how many are left? About 125,000. And now this one, we take 1/2 times 1/2 times 1/2 and put that in your calculator. What do you get? You get 1/8. So 1/8 as much as what we started with. All right, let's do it again. So now we have 0.125. So we did 1 half-life, 2 half-lives. We're going to do a 3rd half-life. So what's our fraction remaining after another half-life? About 0.625, or about 6%. How many years did it take for all of this to happen? How many years did it take to go from 100% down to about 6%, assuming that it's carbon and each half-life is 5,750 years long? Well, this is our fourth half-life. And so about 23,000 years. Oops, let's put that in the right spot. And then how many molecules are remaining? So we currently, at the beginning of this row, we started with 125,000 molecules. How many do we have left? About 62,500. And what would our fraction be here? Well, we did a half times a half. So put all that in your calculator. And what do you get? All right. And then make sure you email Mrs. KJ when you are done. There are some more questions below, but we got through them all in this.